Hi, in this video I would like to show you one very cool little device that I have, and here it is. It's a Morse code keyer. Now the keyer is the name of the devices that generate signals using hand or pressing the key, in this case these two levers. Well, but this is a bit more modern device, so that means there is some electronics inside. There is auto and manual mode, so it will be interesting to take a look at that. But the main goal of this video is to connect this little device to our Commodore 64 and try to capture those signals. Also, besides just capturing signals, we'll try to decode those signals or messages back to the letters according to Morse code alphabet. And we'll do all that in assembly because that's something that I haven't done in a while on this channel. So yeah, that will be interesting. So yeah, Morse code here. Let's begin. Okay, this is our Morse code here, and I removed this outer case so that we can take a look inside. So here it is, and let's firstly take a look at the front. So this device is made by Viking company. The model is SSK-1-K, and we have two knobs. This is for the volume, and this volume is related to this little speaker at the back right here, and we have the speed knob. Now the speed knob is related to this auto mode. I will explain that later. So this device has a little bit of circuitry like you see here, and it does have 555 timer, and this is some logic ICs. So basically, and of course, this is the key mechanism with these two levers. Now, this left lever is represents dots or the short signals, and this right lever is dashes or the longer signals. Now, you can run this in manual mode, so it only sends the signal how you connect these two levers, or you can use auto mode. Now, we have three switches at the back here. First one is for switching the positive and negative signals on this output cable, right? And then we have auto and manual mode. In manual mode, the way how you press these levers, that's how the signals is going to come out of this cable. In auto mode, it's all related to this circuitry and this 555 timer. The speed of repetition of the signals is adjusted by this little knob, and I will show you how that works. So one press of the lever will generate multiple signals. And what else do we have here? We have third switch for switching off and on the speaker itself. So this whole device is powered by 9-volt battery. So to save the power, we can power off this little speaker. Now let me explain something else. Now these devices are meant to be connected to the other radio transmitters and in radio telegraphy. So this is not actually meant to connect to our Commodore 64. So for that reason, besides this connection for the user port on Commodore 64, because we are going to use that port to read our signals, and to be specific, we are going to use first pin on port B. It's not really, we cannot connect this directly to our Commodore 64. Firstly, this is not TTL signal. Secondly, powered by 9-volt battery. This will give us around 7 to 8 volts signals here. For that reason, I use just one line of that whole signal, because this is positive and negative voltage here, and we can change those with this switch. You can switch between positive and negative signals here. Now, I'm not really the expert, but in this position on negative, this red wire will give us positive signal, so that's all that we need. And then we just run this signal through the little transistor. We are using transistor as a switch. So everything here, including this LED, is powered by 5 volts from Commodore 64. And you will see once I connect this to C64, the LED blinking, and we will capture those signals. Of course, we need the ground. This is not the ground, this is the negative side of this signal. So the ground is the chassis, right? Everything is grounded here. It's really nice looking device, even inside. It's beautifully connected. And yeah, old school PCBs without silk screen. Everything is open. Nice. And everything is socketed. That's really interesting. And everything works. Oh, I love these wires. Wow, beautiful. Yeah, so yeah, we will try to power this device and connect it to our Commodore 64 and see how that looks like. So yeah, let's do that. Here we have our Commodore 64. We have our Morse code here connected through this user port card to Commodore 64. I needed to prolong these wires because otherwise it wouldn't fit. We have ISD to IC device so that we can read and save our programs. And we have a microassembler cartridge that we will use a bit later. So all we need to do now is 9 volts battery so that we can power up this little device. So let me do that. And it's powered. So let me see. So we are in the manual mode. So like I mentioned before, this left lever represents dot. And in this manual mode, if I press this left lever, I will always get this short signals. If I press the right lever, which should be dash, it will be lead on as much as I hold on connection. When I let go, it will power off. So that's the manual mode. If we switch to auto mode, and I adjust a little bit of, add a little bit of speed on this knob. So pressing this left lever, these are the short signals or the dots, and these are dashes, you can see. And we can crack it up. These are dashes, and these are dots, so it's quite fast. So let me show you the sound. So we have a little bit of volume. This is how it sounds on dot. And these are dashes. I hope that you can hear that. Woo! Yeah, lots of fun. So yeah, the idea is to try to read those signals, and I will power off the speaker because it's annoying. It's fun, but yeah. I'll explain this separately, but basically, like I mentioned before, this is just NPN transistor, and we open the base of the transistor with the signal from the Morse code here, and then we let 5 volts from Commodore 64 go to pin 0 on port B. That's basically it. And all we need to do now is read the state of that pin and see do we receive any signals. So let me load. I have a bunch of these files. I don't remember. Bloody hell. Hmm. Let, let me do the listing. Yeah. What's the port B1? Port B1. Okay. Load port B1. Yeah, and now let's list this. Yeah, this is it. So this is our little code, and let me explain what's happening here. Well, first of all, we have to define each of those pins on port B. Are they input or output? So we have to define the mode of the pin. And we do that in this register 56579. And all we need to do is change the first bit in that register to be 0. And we do that with ending with 254. Um, so that's the first thing that we need to do. So we define this PB0 as input pin. This variable W should represent the state of the pin, or the previous state of that pin, to be precise. Now the variable D will represent the time, and then here on line 30 we are just reading the state of that pin. So we are reading register 56577, and we are only interested in the first bit, so we are ending it with 1. So variable B will be either 0 or 1. 0 if it's low, 1 if it's high. That's really simple. So now I'm checking whether or not if variable V is equal to variable W, which should store the last state of that pin, and we are checking whether or not the state of the pin has been changed. If not, we are jumping back to the line 30. We are again reading the state of that pin, so we are just looping between line 30 and 40 until the logic has changed, so the state of that pin has changed. In that case, we are continuing, and we are just calculating how much GFIS has been from the previous change. And once we do that, we define variable W to have value of V. And then if the V is 0, so that means in this line 70, we are checking whether or not did we switch from high to low or from low to high. We are only interested to print out values or the timings when the pin goes from high to low. That means that our signal has completed, right? In case that pin did go low, because if you take a look at this, we also need to capture when the pin goes high, when we need to start our variable, counting the variable, right? So then we are, in case that we went from high to low, then we are going to print variable t. So this variable t represents the time of the signal, how long the signal lasted, in GFIS, of course. And then once we print our time on the screen, we are just jumping on line 20. Again, we are starting our timer here, and that's basically, we are repeating this over and over. So if I run this code, nothing will happen until we start pressing her here. So let's try to do with dot. As you can see, we have 6 and 5, so 2 signals. 6 is just 1, 6, and dash, 17, 18 GFIS, 17 GFIS, and so on. And dots are 6 up to 5. And this is just, these values, of course, depend on the speed that we set up on this little knob. Or if we are in the manual mode, then it can go up. Sorry. So the lowest value for the dots is 9 up to 10 GFIS. For the dashes, well, in manual mode, as long as I hold that key down, it will hold that signal high until I release. So yeah, in auto mode, the lowest value for the dashes is 28, 29 GFIS. If I crank this speed up, we can barely see the difference between dashes, dots, and dashes, dots. Yeah, hardly see the difference. So, ooh, 1 and 1. Okay, now we cannot see any difference at all. And this is just too fast for our little basic. Oh, this is this is not correct. It cannot capture all the signals. Yeah, it's skipping the signals. Yeah, unfortunately, we cannot do this in BASIC um, if we are going to um, gain some speed. In slower frequencies, yes, maybe, but let me add sound. Yeah. Ooh. This is. Yeah. So we can see that using this little bit of electronics and two levers, each one for each signal, um, someone who really knows how to use this device can send those messages very, very fast, even with the hand. So yeah. Um, so what we are going to do now is abandon the basic. Of course, we cannot do this here. Um, we are going to switch to assembly. That's why we have this microassembler cartridge. And because it will be very useful or very handy to program our little code, to develop our little code directly on this machine with connected keyer and everything set up. But we do need to do something else to do that. Well, we don't have to do anything, but the way how I intended to use that code, the way how I intended to write that little bit of assembly is it will require additional line here on this to build on this board, and we are going to make external interrupt so that we can capture those signals on in elegant way, not just like here in BASIC, just speaking constantly. No, we are going to build a little interrupt, external interrupt that will tell us when the signal is started, and then we can build from that point onwards the rest of the things that we need. So yeah, let's begin with that. Okay, so this is our user port card. This is our user port pinout. And what we have so far, we use PB0, that's pin C, as input pin. So that's this one. So this is PB0. So that's pin, first pin or pin 0 on port B. And how this is connected, um, simply we use NPN transistor. So, and let me mark, this is the ground, pin 1 is the ground, pin 2 is plus 5 volts, so this is plus 5. So what we have here is our NPN transistor, and we have here plus 5 volts from this pin 2, and then here we have input signal from a keyer. This is resistor. I believe I use something like 2.2 or something like that kilo ohms, just to reduce the current in on base. So yeah, that's that. I don't know how to draw this. Okay, and then this goes through another resistor to ground, just not to make a short, we need some resistor. I believe I use 4.7 kilos or something like that. And on this point, I took signal and connected to VB0. That's about it. So, and on the same point, I connected LED with the resistor and connect everything to ground. So this is that circuitry. So what else do we need? Obviously, this will work just fine, and it does work. But I want to use hardware interrupt on Commodore 64. So what else do we need? Well, the hardware interrupt we have on pin B, and that's called flag 2. So this pin here is connected to CIA 2, and this pin will give us a flag on negative edge. It will create a flag bit in interrupt control register of CIA 2, and this is what we are going to use now. What negative edge means? Well, it means that this pin is high all the time, and then it will trigger a interrupt once it goes low. So this is 0 volt. This change in voltage will generate interrupt. What we need to do, because from this circuitry here, whenever this signal is high, it will produce the high signal on PB0 pin as well. And when this is low, it will produce the low signal. But here we need to generate opposite signal of that. So to do that, we will have to, from this point here, take this signal, or better say here, connect from this point, let's say here, connect this through some small resistor or something, I don't know which one, to flag 2. Oh, that's pin number, that's pin B on here. So if this signal is low, this signal here should be high, and when this signal goes high, this signal should go low. So we have to take signal from here. So if this is the base, this is emitter, and this is collector of transistor, we need to take signal from the collector side, right? So yeah, that's what we need to do. Okay, so yeah, have been a bit silly. So this would not work because we have a bunch of load here. So yeah, don't forget about this. Let's start from scratch. And yeah, I already made a solution. I already built the circuit using another NPN transistor, and now let me draw this schematic as it is. So first of all, we have 5 volts from the Commodore 64, and here we have ground. And firstly, we have signal from the keyer going through, I believe this was like 10K resistor, I believe. I forgot. That's this one, little fellow. So first of all, we are going through first transistor, that already NPN transistor, of course. This is connected to 5 volts, and this goes through another resistor. That is this fellow right here. This is also 10K to the ground. From this point, we are connecting our LED also through 1K, something like that, to the ground. Of course, from this point here, we are going to PB0. That's fine. And now we need additional NPN transistor, but this time we need to pull our flag 2 pin to the ground once this keyer signal goes high, right? So what I have done also from here, another signal that goes through NPN transistor. Oops, sorry. This goes here into the base of this transistor, and this goes directly to the ground. And this line here is connected to flag 2, or that's pin B, and this is pin A, I believe, C. Once we receive our signal, this NPN, this is also NPN, this NPN transistor opens, the current flow through here, so we receive high signal on PB0 pin, right? And then that same signal opens the second transistor, which actually pulls this flag 2 pin to the ground. And that's basically it. And when this keyer is low, this transistor is closed, and this line is closed, and this transistor is closed, and this flag 2 pin has internal pull-up to the 5 volts, so we don't need to do this here. It's already high, so yeah, it does have internal pull-up. So yeah, this is the final final circuit. Yeah, I was hoping to do this with just a single transistor, but yeah, this is the safer way anyway. So yeah, now we can continue further and connect this to Commodore 64 and see what do we have, and try to write a little bit of assembly code. Yeah. So yeah, let's do that. Hi, I decided to split this video into 2 or even 3 parts. I think it would be simply too much to smash everything into a single video, especially later where we're going to write some assembly code, and there will be a bit of assembly code to write. So yeah, every code and circuit or schematics that I've used in this video will be in the description down below. So until the next part, goodbye.